Also thank the organizers and this wonderful tradition of the KITP workshops. I've been coming to these a long time, and this is my first COVID in-person one, so post-COVID, so it's nice to have that over with. And for now, what I'd like to tell you about is at least to introduce things with a fairly old story. It goes actually back to Vincenzo Vitelli's thesis. We were interested in ground states. I'll eventually get to activity and dynamics. But let's talk just a brief review of what's already been mentioned in this workshop about these nice pictures that try to figure out. Here we go. Okay. Yeah. So what we have here is a ground state of a polar vector field on a sphere. So here I drew it on a lacrosse ball, and so you can take a look and verify that you already knew from the lines of latitude that you have two defects, one at the North Pole, one at the South Pole. If I just look at the northern hemisphere and I replace these arrows with double-headed nematogens, the system becomes unstable. And in particular, if I slide over here, you can see that I've indicated that this +1 defect, this vortex vector field, breaks up into two +1/2 defects. That's a lower energy, and you can work out what that energy is on a sphere. And of course, the same thing happens in the southern hemisphere. So I have 4 defects where I had 2 before. They repel each other, and not surprisingly, they go to the vertices of a tetrahedron. So this is shown on a softball, and I'm not going to pass it around right now, but here's an American baseball, and it beautifully can be mapped onto a pneumatic texture. The patent for this baseball is 1861, so I don't know how they figured out all the beautiful geometry and the various constraints of the Poincaré-Hopf theorem, which we've already heard about, but it's there. And of course, in this community, you may all remember this work from 10 years ago by Zeronomir and Andreas Bausch, and I think Mark Boeck and Christina had a role in the theory. And this is an active matter version of this tetrahedral ground state, a kind of topological clock, where you can see 3 of the 4 +1/2 defects, which then orbit around dynamically in a non-trivial way. So this is a fairly simple situation where you have geometrical frustration caused by a uniform background Gaussian curvature, but there's an opposite limit, and that's to concentrate all the Gaussian curvature in, say, the northern hemisphere at the apex of a cone. And so this particular problem leads to my talk. This is an outline. I'll first talk about statics, and even the ground states are, I think, themselves kind of interesting. We'll also talk about the effect of boundary conditions, which can also impose geometrical frustration on a system. And we'll also emphasize that when we look for ground states on cones, here are some cones. This is an active dynamical version, which I'll talk about a little later in the talk. This problem is basically a soft matter analog of the Aronoff-Bohm effect. So many of you, if you learned about this as an undergraduate, this conventional Aronoff-Bohm effect, here's a solenoid, and out here there's no magnetic field. The solenoid screens it out perfectly, but there is a vector potential. And so for 100 years after electrostatics and electrodynamics were developed, for the most part, people thought, well, it's just an artificial construct, a vector potential that's out here that gives you this nice magnetic field inside the solenoid. But then it was realized by Aronoff and Bohm that, in fact, electrons which going through a 2-slit experimental apparatus would have interference fringes which would shift because their phase couples to that vector potential. It would shift by an amount proportional to the intensity of the magnetic flux. And in a similar way, the flanks of this cone for a while, I thought it was fairly boring because they has zero Gaussian curvature. It's very easy to see that. But there is a non-trivial effect of parallel transport. And that will have a somewhat similar kind of effect. It won't be quite the same as interference fringes, but that's sort of where we're going. And then we're going to talk about these defects and on cones, on the flanks of cones, and the effect of activity. And if there's time at the end, I'll tell you a bit about conical billiards. Okay. So these are the people who did the hard work, at least in the initial half of this talk. Farzan Fafa, who, by the way, is on the job market. My former graduate student, Grace Zhang. You can read about some of these ideas here. And let me go forward and just sort of try to tell you why I think liquid crystal order on cones is interesting. It's a kind of problem, or Green's function problem, because as Vincenzo and Ari Turner showed when they were still graduate students, it turns out that defects in general, on a general surface, interact not only with themselves, but also with the Gaussian curvature, which you can think of as kind of a topological charge. On a sphere, it's spread out. It's a uniform charge. But on a cone, it's concentrated. And so by studying cones, we're sort of studying a Green's function problem of a delta function of Gaussian curvature and ask what happens. And of course, there are many examples. There are pine cones, of course, as you can see if you go hiking around here. These are the sort of locally crystalline order, maybe it's hexatic order, on these protrusions in this coral reef. Many of you know about epithelial cells. They can rise up and make sort of concentrations that look vaguely conical. And we also heard a beautiful talk from Yonit earlier, I guess yesterday, about the hydra. And here we have limbs which can end in a delta function of positive Gaussian curvature. And of course, the armpit of the hydra can be modeled by a delta function of negative Gaussian curvature. So we have to try to see what happens when we look at this problem. And important for this talk will also be the effect of boundary conditions. And again, many of you know this, but it's important even on a flat disk. If you take one of these XY models, again, we can assign non-reciprocal dynamics if you wish, but let's just look at at the minimum energy for now before we make things active and so forth. This is a Meyer-Salpa model, if you like, of a liquid crystal. P equals 1 would be polar order, P equals 2 would be pneumatic order, P equals 6 would be hexatic order, for example. And if we take a look at what happens, for P equals 1, well, it's kind of boring. We have these tangential boundary conditions, so let's consider those now. They, of course, impose a non-zero line integral of the gradient of the phase as I go around. But just like the northern hemisphere, when we went from polar to pneumatic, this thing at the center will split into 2 plus 1/2 defects, shown here by these little triangles. And in fact, you can show, as Farzan was able to show just by kind of analogy with electrostatics, you put an image charge outside this disk to satisfy the boundary condition, and then you minimize the energy, and you can find out where these sit as a function of P. Okay, so that's a disk, but what we want to do is imagine that this disk, this apex of the disk, will erupt into the third dimension to make a volcano-like structure. And you'll see that if you regard these plus 1/2 defects, there's 2 of them here, as kind of the offspring of the apex can eat its own young. And so as I go off into this third dimension, interesting things, dynamical things are going to happen, which I'll get to in a couple slides.
Yeah, I have a question.
Yes, please.
What prevents the defects from escaping from the
boundaries? Oh, thank you very much. The question was, what prevents the defects from escaping? It's the tangential boundary conditions. And it turns out, with the boundary conditions are in tangential, the image charge out here is the same sign. And so they are trapped inside the disk. If I had free boundary conditions, their image charge would have the opposite sign, and they would just flee and go out to the edge. So thanks for that question. And please do interrupt as we go along. Don't hesitate to ask questions. Thank you. Any other questions? Moment. Okay, so this is just a primer on the differential geometry of a cone. And we'll look at parallel transport and various other things as we go along. So this is just one representation of how you navigate around on a cone if you're an ant crawling around a cone, or a beautiful starfish embryo moving in a conical geometry. Then there's a cone angle beta, which is going to play an important role in what I have to say. And there's a metric, but it's diagonal and it sort of looks locally flat. Indeed, the Gaussian curvature is everywhere 0 except at the apex. And one of the nice things about a cone is that you can show that if you take any circular path, it doesn't have to be a circle, and you go around here, go around down here, go around in an irregular path, anything that encloses the apex, just like the Aronoff-Bohm experiment, the integrated Gaussian curvature inside is a constant. And in fact, you can show that it's given by 2 pi times 1 minus sine beta. Beta is the cone angle. And we sometimes write that as 2 pi chi. Chi is the fraction of the removed area that you would have if you cut out a wedge in a disk and glued it back together. Okay, so that's again, that's like the flux going through a solenoid. And now this is parallel transport. So I'll show you that many of you have seen me do this. I just enjoy doing it. It's a demonstration from Sidney Coleman of parallel transport, not on a cone, but on a sphere, if you approximate my head by a sphere. So I'm going to start here on my nose. I will now parallel transport to the top of my head. I now come down to my ear. I come back again along the geodesic. Rotates by 90 degrees. Rotates by an amount proportional to the enclosed Gaussian curvature of a sphere or any spherical object. It's a topological thing. Here we have a delta function of Gaussian curvature. And if you do the same thing, indeed, for
Can I interrupt?
Question, please. Yes.
Yeah. So is it true for any surface with the Gaussian curvature 0, but a singularity in the curvature at some point?
It's true for all the cones I will be talking about. It's definitely true.
Okay.
Yeah, absolutely.
Okay.
Absolutely. Thank you for the question. Okay, and so here I've illustrated this little parallel transport. This is a chi equals half cone. And so if I just parallel transport this thing around, it's not going to come back to itself. It'll rotate, in this case, by 180 degrees. And of course, we don't have to subtract area. We could add area. And in this case, we'll get, again, an interesting thing which we call a hyperbolic cone, where I've added area. And again, this is everywhere flat, except for a delta function of negative curvatures, like changing the sign of the flux in the Aronoff-Bohm experiment. So now, if I want to understand mathematically what's going on in this situation, it turns out those Myers-Salpo models, all you have to do is add a little vector potential on every link to describe the Christoffel symbols, which will rotate the order parameter as you move around on this curved surface. And turns out to be, these are the components in polar coordinates. It's a kind of conical Aronoff-Bohm effect. And if you just try to minimize this kind of energy, or this kind of energy here, depends on the value of chi. That's like that's the intensity of the delta function. Pointy cones rotate order parameters more than more gentle cones, and then for various fractions of 1/6, you can see the amount of rotation. I now want to just, as a warm-up to introducing activity, talk about, what is the ground state of this thing? Because if I just try to calculate a ground state by minimizing this absolute value squared, that seems like a plausible approach. Locally, I integrate the phase, and I come around, and there's a mismatch. And so the problem of trying to find the ground state is basically trying to minimize the energy of a stack of maybe a strip-like textures that are tiling the walls of this cone. Though it's a somewhat non-trivial problem, and what we've done, both theoretically and numerically, is study these cones as a function of chi, Numerically, there's a special set of cone angles that will allow you to perfectly tile with a triangular lattice or a square lattice. So those are useful for the numerical calculations, but we can talk about a continuous family of cones varying chi. And interestingly, if I go back to that disk problem, turn it into a cone, tangential boundary conditions are going to themselves be affected by this desire for parallel transport. And so this is the tangential boundary conditions, but if I just let the parallel transport act on it, you're going to violate those tangential boundary conditions. So there's this tension between tangential boundary conditions at the base of a cone and parallel transport. And so we actually went and minimized the energy. Grace Zhang was the person who did this. Over here I have some various set of models that are going to illustrate some of the things I'll tell you. And so here's a ground state of a pneumatic liquid crystal sitting on a cone. Well, you can see that there's tangential boundary conditions at the bottom. And here's the baseball that I talked about. So we could imagine going to this cone in another way. Take the northern hemisphere of this baseball and pull it into a pointy cone, just the northern hemisphere. You can preserve the tangential boundary conditions. If you look at the northern hemisphere of this baseball, maybe I'll pass it around now, you'll see that there are two defects in the northern hemisphere, two defects in the southern hemisphere, not surprisingly. And so, you expect that if you pulled it, at least gently, there'd be two defects. And if you look here at this cone, there is a +1/2 defect. Much like the +1/2 defect on this cone, paper cone that I'm going to be handing out. Okay? On the other hand, if you look on the far side, one of the defects has disappeared. It's gone. And in fact, you maybe won't be too surprised to learn that the apex has decided to eat it. And if it's a pointier cone, it'll eat both of them. So in contrast to a hemisphere that is in the baseball, there's actually, in this particular case, I think it's chi equals 1/2, there's only one defect. And if you keep going, as I said, here's the disk with the tangential boundary conditions forcing in these defects. As someone asked, they can never escape with tangential boundary conditions. They're image charges of the same sign. And then this apex has eaten one of them. It happens everywhere between chi infinitesimally above 0. The slightest cone will begin to eat, and then all the way up to 2/3. There'll just be one on the flank at a position which we can calculate. And then for chi greater than 2/3, if you remove more than 2/3 of the area in this ground state problem, you will discover that, in fact, it has eaten both. So we've heard about the Poincaré-Hopf theorem, right, on something with a spherical topology. Imagine a bicone. That has a spherical topology. Well, it won't have 4 defects, at least if you ignore what happens at the vertex. So I would urge you to take the Poincaré-Hopf theorem with a grain of salt. Of course, they had smooth assumptions about their surfaces and so forth. But it eats them, I think, in an interesting way. And in fact, Cheng Long, that's a picture of Cheng over here, has studied, and Farzan Fafa and Grace Zhang have worked on this as well, what happens as a function of chi when you look over these things. And in fact, you can take a look, let's say for p equals 2 pneumatics, and try to figure out the ground states are. And so this is what we've just been talking about for conventional cones. This is a hyperbolic cone. And I'll pass that around. Now this is a little more encouraging. The apex has given birth to a 3rd defect. And so as a function of the magnitude of negative chi and positive chi, there are these sort of micro first order phase transitions in the ground state. And even p equals 1 can have a defect that's displaced from the origin for negative chi, as Cheng discovered. Question, please. Yes.
Yeah, so I was wondering, so you're talking about the total ground state here, but
Yep.
I could imagine that this is a metastable system, or
Yep.
sort of in the dynamical systems lingo, a bistable system.
Absolutely.
Right, where if I start with two defects,
Yep.
even if chi is still smaller than 2/3,
Yes.
they would both survive, and one would,
Yeah. Thank you.
both might be absorbed. In that
Yeah,
case.
excellent question, and it is observable. So we find these ground states numerically by heating things up and then annealing down, and 95% of the time we'll get what I call the ground state. 5% we get 5% of the time we get a metastable state. So that can certainly happen, and you'll see that that comes back. That issue comes back with a vengeance when I introduce activity. For this hexatic, there are 6 defects when you have a disk with tangential boundary conditions, and then for positive and negative chi, it has 6 children that it can eat in a sequential fashion or give birth, etc. That's the statics, but this is a conference on active matter. I would love to talk about active solids on cones, and there are some interesting things involving grain boundaries. I won't have time to tell you about it, but this is some work with Amin Dost-Mohammadi and Farzan, where basically they wrote down the simplest model, or experts in the audience who know more than I do, about these active pneumatics, but on a conical structure. And here are the various terms that you can find in these papers with molecular fields and rotation and shear terms, and then there's a background fluid, and we assume there's some friction, and so at long wavelengths that friction will be pretty simple. And Farzan invented a very nice conformal mapping that allows you to replace conical problems with planar problems with a non-quantized defect charge at the center. So he and Amin applied that trick to this problem, and this is fancy complex notation. Don't worry about the details. It's just implementation of these equations up here, and we take the simplest case where we have the activity, an activity parameter that makes these things move and do interesting things. We chose alpha to be positive and looked at an overdamped limit. No noise. I know Julian will ask about noise if I give him a chance, but we haven't done that. But here's a very simple situation where now we have a disk. So this is starting with the disk. We have some activity, and here we have those two plus 1/2 defects. And if I run this thing, you can see they start orbiting around. They can't escape because of the boundary conditions. Here I think there was a 45-degree boundary anchoring condition at the wall. So they move around, they do interesting things, but this is just a disk. So now if we make it into a cone, so I can go forward here, now I have a certain value of chi. I've removed 45% of the area. And we're going to see we have a 3-body problem here, effectively. We have these 2 plus 1/2 defects, but now this is a conformal flattening of the cone. But it's not obvious, but there's actually effectively a defect at the center. You'll see it coming into play. So it's a 3-body problem. And we can watch and see what happens in this active case. And you can see one of the defects gets eaten, but the other continues to orbit. But this is relatively small activity. You can get some insight, as Farzan did, using a kind of active matter Born-Oppenheimer approximation. So the Born-Oppenheimer approximation is a way of doing quantum mechanics and doing chemical bonds. And how many of you have seen the movie Oppenheimer? And okay, probably everybody. There's a point where somebody comes up to this young guy and says, "Oh, I really love your theory of the chemical bond." Well, that's what this is doing for us. We're saying that the texture can relax almost instantaneously to the locations of these plus 1/2 defects. That's only an approximation, but it seems to work reasonably well. Okay, so now I'll show you the last of these activity movies, where now chi is 3/5. It's fairly big fraction of the cone removed. Larger activity, and you'll see that we don't have a 3-body problem, we have a 4-body problem. And again, there's 45-degree anchoring at the boundaries. And so as I move this thing, well, it happened pretty fast, but I'll run it again. Something interesting happened at the apex, and you'll hopefully see it. There we go. So take a look at this thing. This apex has emitted a -1/2 defect, which, like a killer drone, seeks out the +1/2 defect and destroys it, leaving behind some extra defect charge at the. So this is a picture of a snapshot of what's going on. So this is, and in fact, if you run this thing long enough, you go with 2 defects on the flank, and then the killer drone comes out. You have 1, then it goes back to 2, and it does something erratically. I have 5 minutes left. Thank you very much.
David?
Yes, question.
Is the unbinding here at the apex due to activity, or would this also happen if I do this in a purely passive system and I start it in the same initial condition? Yeah, so it's a little bit like, thanks for the question, it's a little bit like the stuff that you may have worked on. I know Christina and Shiraj Shankar have worked on it, where activity tends to rip charges of opposite sign apart. So here I have like a lightning rod at the apex of the cone, and the activity helps you rip things away that wouldn't be present in actual, in the absence of activity. So thank you for the question. So if I can summarize this part of the talk, I have 5 minutes left to tell you about chaos, conical billiards and chaos. This is a summary of what's going on. You can actually, as Farzan and Amin did, do a reasonable theory of what's going on. And this is a function, as a function of this deficit angle, it's a kind of phase diagram of the dynamics that are seen on the flanks of the cone and activity. And the segue that I need up here is above this wiggly line. They were a little afraid to go because that's chaos. And so this lightning rod seems to be spitting out and absorbing ±1/2 defect charges in a seemingly random way up here. So I wish I could tell you a theory of that, but I can tell you in the last few minutes about some unpublished, very recent work by Laura Braverman, who worked with Vincenzo at Chicago and is now my student. And what we thought we'd look at was a simpler problem on a cone, however. So we started with a cone and we said, suppose I had a conical waveguide and I looked at geometrical optics inside the walls of the cone. So geometrical optics would presumably send light rays on geodesics, but they would be influenced by this delta function of Gaussian curvature at the top. And before anybody asks, if you cut off the tip of the cone a little bit and you stay away, nothing changes. It's just a little. It's just like changing the radius of a solenoid in the Bose-Marinoff effect. Basically, it's a little bit of a snip. It doesn't matter. Anyway, you can start with just a geodesic path. Geodesics on cones are like boomerangs. If you try to shoot at the cone apex and you're a little bit off, it goes up and it wraps around like Halley's Comet and it comes right back at you. And what we had to do was bounce with angle of incidence equals angle of reflection at the base. And what it does in this case, it never gets closer if you're misaligned in this initial shooting than a certain amount to the apex. And don't worry about all this math. But Laura could calculate this is like a caustic in geometrical optics, how the intensity of points visited for incommensurate angles incommensurate angles alpha, how it diverges. It diverges like a square root. Okay, I want to finish. And this is the details. But now, that's not chaos, right? I mean, just says it can never be ergodic because I'm not going to be able to, sample. If this were a particle bouncing around, maybe I want to do statistical mechanics. But it better be ergodic for me to do that. And here it's not visiting all of phase space. Clearly not. But what Laura discovered was if you look at tilted cones, something happens. You still have all this parallel transport, But now the base of the cone is an ellipse, but it's not like elliptical billiards. It's on the walls of the cone. And what I'll show you in this movie as I wrap up is we're going to start with an initial condition here, which is a kind of a cluster of particles that are going to be emitted here, and they're going to come out, they're going to bounce off the wall here. Angle of incidence equals angle of reflection. This is an unrolled cone. It's just an easier way to think about things. Then I have to worry about this parallel transport singularity along the green line. So when they hit the green line, they're going to be rotated by an amount which is 2 pi chi. So these are all very close together. And now for these, this tilted cone, gamma measures the amount of tilt. You can see what happens. Conical billiards. And seems like it's getting pretty chaotic. And so there's a Lyapunov exponent that Laura measured. And I'll pass this around as well. So this is a tilted cone, and for those of you who are not near the front, the trajectories here are uniform. So you can do statistical mechanics on this, provided chi is large enough and gamma is large enough so that you get a transition to chaos. It seems to be, I don't think it's been looked at before, but I think this conical billiard problem is really cool, and there's a pathway to chaos that we're trying to understand involving Poincare sections, a lot of cool dynamical system stuff, which you could in principle imagine studying, maybe look at the motion of a defect, an isolated defect with weak interactions with everything else, or you could just look at geometrical optics and look at conical waveguides. So with that, I will stop. This is a very pointy cone. This is the boomerang effect. I start off down here, and I go around and around and around. Don't make it to the apex. I bounce back. It comes right back at me. So with that, I'll stop, and thank you for your attention.
All right. Very nice, David. We'll start over here.
Hi. Beautiful talk. I'm very curious, in this cone where you have the active defects and you see the plus 1/2 defect getting trapped at the
apex.
At the apex.
Yep.
This reminded me of, this work that we did with Siraj on defects in spatially varying activity. One thing that we noticed was that plus 1/2 defects tend to get trapped in local regions of very high activity, where there's a high curvature in the activity gradients. Okay. Do you think there is a way to map, like taking these, this like flattening of the cone and projecting it and looking at the defect dynamics? Is there a mapping between, say, the dynamics induced by curvature on the cone? Could you map that to a flat space with a particular activity profile, so making alpha a function of space? Is that something that you guys have thought about?
Well, I've thought briefly about it. It's a very interesting idea. I don't know exactly how to do that mapping, but one maybe could play around and find an equivalent space-dependent activity. I'd have to think about that. This cutting the cone open, it's a little bit like a solenoid. If you try to look at arguments about magnetic monopoles, there's a Dirac string that comes out. The analog of that Dirac string is the cut that we make to unroll things. And so we put all the parallel transport stuff along that cut. Maybe if you had activity with the jump discontinuity, it would work. It's a very interesting idea, but I unfortunately don't have more to say about it.
Thanks.
Yeah, this is really fun. So you mentioned the AB effect from the beginning, and I'm wondering what is the analog of that in what you talk about.
Sorry, I mentioned at the beginning, what, sorry?
The AB effect.
Oh, RF boom. Well, so the idea is that the analog of the flux through the solenoid, which is all you need to determine electron interference, is the intensity of that delta function of Gaussian curvature at the apex. Now, one way where this is quite different is positive and negative flux through a solenoid is the same by symmetry, by time reversal symmetry. But I can assure you these hyperbolic cones are vaguely similar to conventional cones, but they're very different. So if you switch the sign of the flux, that's going to negative Gaussian curvature. there's a manifest asymmetry between positive and negative Gaussian curvature in the stuff that we've been looking at. So the analogy is nothing more than that. Vector potential outside a solenoid has a zero curl. Gaussian curvature is zero on the flanks of the cone. But if you go around the apex or you go around the solenoid, that integrated vector potential makes a huge difference. That's sort of the take-home message.
Yeah, I guess a simpler analog could also be if you send a transverse wave packet from one side and they meet at the other side.
Absolutely, and you could send a wave packet. I mean, we'd love to do quantum chaos on a tilted cone. You know, I like H-bar too, and try to figure out what happens with that. You know, another thing that I'm hoping to persuade the experimentalists in the audience, maybe Nikta, maybe somebody else, you know, in the Olympics you saw these bicycle races on a tilted track going around and around. It kind of looks boring. But those races are being held on the walls of a cone. And so as they go around and around, hit quinky rollers on a bank track. That might be another thing that this community could be interested in, among your many other interesting subjects.
Yeah, this is probably already known, but can you write the effective stress tensor for a pneumatic order on like curved surfaces, just using the idea of vector potential?
Well, we heard earlier this week a very nice talk where you generally have a curved surface, and it's a smooth curved surface, and there's a metric tensor, there's a curvature tensor, and you can have various coefficients that relate that to the strain tensor or the stress tensor. And a cone is similar, but locally it's flat. And so you need to put in a few judicious sort of parallel transport terms, but in a sense it's an easier problem, but nevertheless has this, you know, chaotic dynamics of defect emission and absorption, etc.
Thanks.
Yeah.
Hi, great talk. So, like in the example you showed, where you have this lightning rod, which the defects come out, and the activity there was not quite as high to have like active turbulence, right? So it was active, but just enough for the defects to move around and have this effect.
Yes.
What happens in the active turbulent regime?
That's a great question. I think my guess would be it's the analog of dielectric breakdown, where you have a lightning rod with such an intense voltage, it produces plus minus pairs and
okay, I see. So it will be produced by the lightning rod and not like usually at random positions.
That's right. It wouldn't. So another question, which I think you're alluding to, is what is a Costulus-Fowlis transition for an XY model, even in equilibrium, on a cone? I would love to know what happens for non-reciprocal system XY models on a cone as well. But even that is a challenge. There's a kind of Debye-Huckel theory that you could import into conical stuff with a defect at the center using Farzan's ideas, and there can be defects ripped apart on the flank at finite temperature, maybe at finite activity. I don't know. So we hope to look into that.
Coming back to the
noise.
Coming back, no noise. Coming back to the transition to chaos.
Yes.
So when you take elliptic billiards and you deform them,
yep.
The transition is very interesting. You have separatrix.
Yep.
You have a set of chaotic trajectories that make up the Arnold wave, which is a measure. So in this case, is it very different? I mean, what type of transition do you have?
Well, okay. Thank you. So the question is alluding to a wonderful, well-developed body of knowledge about elliptical billiards, which can be turned into a stadium model, and there's a control parameter there that people like Sinai and others have worked on. So what seems to happen when you transpose this into a cone is a path to chaos, a non-trivial path to chaos, and what I show up here, I won't pass them around because everybody wants to eat lunch, but basically there's an analog of these orbits. We call these box orbits that would go between the foci of the ellipse. And there's an analog of the ring orbits that would go around the two foci. But as it gets pointier and pointier, you go off into this different chaotic regime. Eventually, you paint the surface of the tilted cone for large enough tilt and large enough chi uniformly, and it looks like it's ergodic and mixing, and you could do statistical mechanics, but not for all cones, just tilted enough. So, very interesting question. Still looking into it. It's not quite the same problem as conical billiards, but it certainly can learn a lot from this nice elliptical work.
And so you get a progressive transition of the chaotic set as you increase the tilt?
It seems to be. It seems to be, and we get all sorts of interesting. So what's shown here, see, each time over here on what you're seeing over here is the unrolled tilted cone. And this unrolled tilted cone has all sorts of possibilities. The orange things are the initial conditions. Here it bounces around. It never actually gets close to the apex. Here it's this box orbit that's sort of between, it would be between the foci if it was actually an ellipse. It's not. And then we have these mixed orbits. So if you look at, so what this Poincaré section is, what Laura looked at was, you know, each time it bounces, you get a new line, a new geodesic line on the unrolled cone. And this is kind of a way of representing these lines with a y-intercept and a slope. And this green thing, that's a box orbit. This is one of these loop orbits. And then this is the beginnings of chaos. We think.
All right. So, question over there, and then I think I'd like to ask the last question.
Of course.
Thank you. Thank you, David. So I have a question about the time reversal symmetry breaking. So when you introduce activity to the system, there were, let's say, different ways of thinking about time reversal symmetry breaking depending on, let's say, the geometry. For example, when you have circle, the two defects are basically rotating in this chiral direction.
Correct.
But when you have cones, especially when you have high activity, then I can think about the number of defects as, let's say, some state. And there will be some transition probably between the state, and probably it seems to like break detail balance, let's say. And
yes.
Do you have any, let's say, ideas for how this kind of, let's say, representation can be interesting anyways? Or?
Well, I think it's interesting, but I don't have any deep insights. Yes, there's undoubtedly something happening that involves the orbiting. And the orbit for us in the simpler versions where there's modest activity is determined by the boundary conditions and the sign of alpha. You know, this beautiful stuff that Sriram and others have worked on is that determines the direction of rotation. But in general, you know, there's this strange, it's almost like telegraph noise where you have emission, absorption at irregular intervals. And that's terra incognito, at least for us at the moment.
Thank you.
All right, thank you.
Deb.
Yes, so beautiful talk. There's a lot of questions I could ask you. The one that most came to mind is years ago now, Mark actually was telling us about defects in liquid crystals that interacted with vertices that form dynamically. So you have this thing where the you know, the conical vertex is invulnerable and it's killing these liquid crystal defects. Have you thought at all about allowing the conical vertex itself to be a dynamically forming thing and having?
Well, it's a great question, and we you know, as you've realized from the very beginning, we just simplified things by freezing the surface. But we saw in the earlier talks this week that you know, these beautiful biological systems, they may not like this particular cone angle, and they may start dynamically changing chi. Yes. So chi should be a function of time, and that's a beautiful problem. We thought we'd freeze the geometry and see what happened, but I hope people will move in that direction of allowing the shape to, as Mark studied, the shape to change. And in fact, there are preferred cone angles that seem to have an especially low energy. Most of the time, the energy, at least in the equilibrium stuff, diverges logarithmically with some coefficient. There are magic cone angles where that coefficient vanishes.
Yes.
So you'd think that those magic cone angles, maybe they play a role, or the arms of a hydra would like to be at that angle. I don't know.
All right, great. So let's thank David and let's thank all of our speakers.